Hello everyone, welcome back to day 10. We're going to continue talking about sorted edges, but we're going to talk about it in the format of tables today. We introduced the sorted edges technique and used it to find efficient Hamiltonian circuits. However, a lot of the times when we receive information about networks, we don't get a nice pretty graph that is displayed for us. Instead, we have to create a graph. So today we're going to focus on reading a table, which is probably a more common way to display information about networks, or actually network graphs and things like that. So we'll take a look at the table, and then I'll show you how to take that table, set up a graph, and use that graph to find a Hamiltonian circuit. All right, so I recopied the sorted edges algorithm here just to remind you of how sorted edges works, and then we'll take a look at an example. Right. So here in example 1, this is how they would give us a table, and what we're seeing here in the table are the list of vertices here at the top. So if I wanted to start building my graph right away, something I could do is I can come over here and just start putting my vertices on the paper, right? So I know I'm going to have a vertex A, a vertex B, I can put like vertex C, and it doesn't matter where you put these vertices at. You can put them anywhere. Right. So there we go. So there's all of my vertices A, B, C, D, E, and F. All right. So for instance, this first number that we see here indicates an edge, right? That there is an edge that connects A to B, and it has a length of an 11. So I could draw an edge from A to B and mark it with an 11. All right, but since we're doing sorted edges, really all we want to do is we want to add the edges to our graph in the order of their expense. All right, so if we recall, the algorithm says to add, right? It says select the cheapest unused edge in the graph and add it to your circuit. So I'm not going to draw in every single edge here. Instead, what I'm going to do is I'm only going to draw on the edges that I'm going to use for my circuit. All right, so since the sorted edges requires us to pick the cheapest edge every time, we're going to go down here. I notice that the cheapest edge is 10, right? And that goes from A to F. So I'm going to come over here. I'm going to draw an edge going from A to F, and I'm going to put a 10 on it. So this is the first edge that's going to be in my circuit. And you'll notice that there's a lot of repeats. And the reason being is because this is the same circuit, or the same edge going from F to A is the same thing as going from A to F. Right, so really the bottom half of this table, we don't really need it. It's all repeat numbers. So I'm just going to scratch those out. This makes it a little bit more manageable. And I'm going to cross off the 10 because I used the 10. All right, so then I scan the table looking for the next cheapest edge. And here it is at A to B, right? So going from A to B. And that one has a cost of 11, right? So we start to see our circuit take shape here. I'm going to cross off the 11, and then I scan the table for the next cheapest edge. That's going to be this 12, and it goes from B to F. All right, so if I go over here, if I were to draw in this edge going from B to F, that would complete a circuit, and that's something that we're not allowed to do when we do sorted edges, so we don't want to complete any circuits. So 12 is not able to be used here. That edge going from B to F, we would not use it. So I'm going to go ahead and cross it off and move on to the next cheapest edge, which is going from B to C. All right, so B to C would be okay. And it's got a cost of 13. So I'm going to put a 13 on there. And we'll cross off the 13 and rescan. Right. Next cheapest edge is 18 going from C to D. Okay, so if I connect C to D, that shouldn't cause any problems. No degrees of 3 and no completed circuits. Right, so 18. Cross that off, and then we rescan looking for the next shortest edge. Looks like it's going to be this 24 going from E to F. So there's E to F. I don't see any issues with adding that into our circuit. So there we go, and I'll put that 24 on there. Awesome. Next is going to be the 25 going from D to F. So here's D going to F. That would create a problem. That would make F degree 3. Can't do it. So we can't use the 25. All right, and then we go to the next cheapest edge, which looks like it's going to be 30. I don't see anything shorter. So that's going from B to E. So let's see, B to E, that would create degree 3 at B, so we can't use that one. 33 looks like it's next, so going from A to E. So A to E, that would create a circuit that doesn't include everything, and it would make A degree 3, so that's really bad, so no no A to E. Next up, 35. All right, so going from C to E. Let's see here. Nope. All right, that would create a degree 3 here. So I'm going to cross off the 35. Move on to the next one. Looks like 47 going from A to C. So that would not be good either. That creates 2 degree 3s. Next up, 49. So A to D. Nope. All right, that creates a degree 3 here. And then we go to 57, so this one's going to be B to D. Oh, wait, 55 was the next shortest one. So this one goes from D to E, and I think that's the one we're looking for. There we go. And I'll put a 55 on there. And that completes our circuit, and that's okay because this circuit includes all of the vertices. All right, so 55 was the next one used. So the next thing we want to do is we just want to describe our circuit, so you can just go in order around our circuit here. So we can say A, B, C, D, E, F, and back to A, and then add up your edges to see what the total cost of the trip is. And I think if you add this one correctly, you should get 131. Okay. So that's how you go from table to your graph. And notice I didn't draw the entire graph. I didn't draw in every single edge that existed. I didn't draw in any of the edges that would have ended up in the middle here because all I wanted to do was represent my circuit, right? So I only added the edges I needed for my circuit to my graph. All right. Okay, and we're going to try this one. And this one's a little bit more complicated here. It's got a lot more stuff going on, but the context of this problem is that there is a band that is touring in Oregon, and they have to go and do shows at all of these cities that we see listed here across the top. So they have to travel to each of these cities once and then return home to wherever they started from. It doesn't even tell us where they started from because it doesn't matter, because whatever circuit we come up with, we can start the circuit at whatever point. All right, so I'm going to do this. I'm going to take the same approach that I did last time. I'm just going to take all of the cities. I'm going to arrange them here in a nice circular graph. So I've got all of my vertices, so all the cities that I need to visit. And then I'm going to get rid of the bottom half of the graph because they're all repeats. So I don't need anything down here. All right, and as we do this, I know it looks like a lot, but I'm going to show you a couple tips and tricks to minimize some of the work here. All right, so here we go. All right, so here we go. So I've got all my vertices arranged over here, and what we're going to do is we're going to go through all of our edges. We're going to find the shortest or the cheapest edge first, and we're going to add that particular edge to our network graph over here until we have a completed circuit. So here we go. I think the cheapest edge here first is going to be Astoria to Seaside. So I'm going to go to my graph over here. Here's Seaside, here's Astoria. I'm going to connect those two and label this with a 17. Okay. And then I'm going to cross off 17. It has been used. All right, so then you would scan the table and you would repeat the process again, looking for the next shortest edge. So that's going to be the 40 here, going from Corvallis to Salem. So here's Salem, here's Corvallis. I'm going to connect those two, label it with a 40. 40's gone. All right. Then we go to the next shortest one. It looks like it's going to be 47, but we do have two 47s here, okay? And I don't think for this one it's going to matter which one we choose to do first here. So I'm going to go with this one from Portland to Salem. I'm going to do that one first. So here's Salem, here's Portland. I'm going to connect it, and I'm going to go 47. And you'll see why it doesn't matter here in just a second, because the next shortest edge is obviously going to be the other 47, which goes from Corvallis to Eugene. Right, so Corvallis to Eugene. So it would have just been adding this one and then this one, or this one and then this one. It wouldn't have made a difference in what order we had done that in. Okay. Now, a couple of things I want you to notice. All right. Notice that Salem and Corvallis just reached a degree of 2. All right. We cannot draw any more edges going into Salem or Corvallis. So pretty much everything here in the Salem column we cannot use. Right, so none of these can be used. And then same thing with the Corvallis, right? So Corvallis is now at a degree of 2, so these are all gone. Okay, so it's like we just eliminated a whole bunch, right? By noticing like, hey, these are degree 2, anything coming into Salem we can't do anymore, anything coming into Corvallis we can't do anymore. All right, so the next edge, if we scan our table with what's left, the 52, right? The 52 would be the next one, but notice, hey, that's Corvallis, right? Corvallis to Newport. So if I go over here and I try to add Corvallis to Newport, it would create a degree of 3. So not only can we eliminate this vertically, we can eliminate the entire row with Corvallis in it. So we can eliminate all of those. Okay, so those are now all gone. All right, and we could do the same thing with Salem. Right, so Salem's way down here. We can actually get rid of this 118 down here. We don't need that. And we're going to move on and start scanning for our next shortest edge. So the next shortest edge would be, let's see, 78. I don't think there's anything shorter than 78. So we got Portland to Seaside. Right, Portland to Seaside. We can do that one. And it's got a length of 78. Now notice Portland just went to degree 2, so I'm going to get rid of all these. And Seaside just went to a degree of 2, so all of these. And let's see, so we can also go horizontally here, so we can go Portland, which is down here, so those are already eliminated. And then Seaside was the other one. There's nothing down there. All right, so starting to narrow it down. So after that we've got, let's see, start scanning this table again. That's the most annoying part, is having to go through this trying to find the next one. All right, so let's try this 91. I don't think there's anything shorter than 91. So this one goes from Eugene to Newport, and that one we can do. So I'm going to add that 91 to my graph there, and we can kind of see this thing taking shape, which is nice, right? So Eugene just went to degree 2, so everything here we don't need, and everything here, right? So that 91 got eliminated, which is fine. And so keep going. Look for the next shortest one. Okay. Oh, there's a 108. All right, so let's see, 108, which is Ashland to Crater Lake. Here's Ashland. Here's Crater Lake. They're both degree 0 right now, so let's connect them. And we'll put a 108 on them. There we go. So nothing went degree 3, so we can't eliminate anything but the 108. We just use the 108. And we go to the next one. Let's see if we've got anything shorter here. So I think the 135 is next. This one goes from Astoria to Newport. So let's see what happens if I go Astoria to Newport. Oh yeah, we can't connect that one because it would actually complete a circuit. That would complete a circuit that did not include Ashland and Crater Lake. So 135 is going to get eliminated there. We can't use that one. So I think the next shortest one is actually the 180 going from Bend to Newport. So let's check that one out. Yeah, that one we can do. So Bend to Newport. And so now Newport went degree 2. So the entire column with Newport gets eliminated there. We don't need anything from Newport anymore. And going this way, we got that. Okay, so again, scan for the next shortest. I think it's going to be the 200. All right, so I'm at Bend. We're going to go to Ashland, and we can do that. They're both degree 1, but now they're both degree 2. Okay, so Bend and Ashland, done. And there's nothing over here for Ashland. And we can eliminate everything here. So there's only 2 routes left. There's the 374 and the 433. So going with the 374 here, looking at Ashland to Astoria, but Ashland's already degree 2, so we can actually eliminate everything in this row. So the only thing left is the 433 going from Astoria to Crater Lake. So yeah, that would connect these two, and that makes sense because they're both degree 1. That would connect those. That actually completes my circuit. It's an expensive edge, but it is the only one we can choose. All right, so there we go. That is our completed circuit. If you add up all of the edges in your graph here, I believe you get a total of 1,241. Okay, so this would be our total trip distance using this circuit up here, and you could abbreviate these however you wanted and write out your circuit in order. You can go forwards or backwards through your circuit, it doesn't matter. All right, guys, so that is cheapest edge from a table. Give the practice problem a try and let me know if you have questions in the Zoom chat. Have a great day.